safety critical aspect of FPGA. Um, and it's not so much of just checking the FPGA functionality, but there are additional requirement, additional certification that you might have to incorporate in your product from a safety critical standpoint. Okay, so we will go through all of that stuff. So at this point, I'm gonna hand over to Walter and make you the host. Okay, so go ahead, Walter, and share your screen.
You should be seeing my screen at this point.
Yeah, I see the. Nope, not yet.
No.
Okay. Actually, I do see it. Yes, I see the first slide. Yeah.
Okay.
Yeah.
All right. Excellent. So as Kong said, today's webinar is going to be on safety critical design, and we'll touch on a few products from Mentor that are used in our safety critical solution. So my name is Walter Goody. I'm an applications engineering manager at Mentor Graphics, and I handle most of the functional verification. So pretty much any front end FPGA design and verification tasks are handled by myself. So safety critical design, in general, what is it? Why is it important? And it basically started out, I would say, maybe a decade ago in the aerospace world, and really in the civil aviation world, with the DO-254 standard was kind of the first safety critical standard that was applied to an industry for FPGAs. It fairly quickly, well, it took a little while to catch on in the civil aviation world before they were really applying the principles. But then once that happened, it fairly quickly moved into the from civil aviation into the mil-aero world, and then into the medical devices world, and now the ISO 26262 for the automotive world. We're seeing it in the banking world, in the trains, any kind of a transportation system. We see it in space flight, where it's called mission critical. So if the device fails, the mission fails. So we are seeing that safety critical is a growing set of standards. So, you know, just a little background. Does any of this sound familiar? That you're not really planning, you see your schedule slipping, you don't really know where you are in the process, you're fixing a lot of bugs fairly late in the design cycle, the product has some issues in the field, and these are all symptoms of not following a safety critical system, a structured design system. And so it's really the ad hoc, which is that the project is not necessarily really well planned out. Tom, can you look and see whose microphone is still on and muted? So, you know, we're talking about an ad hoc structure where things are not necessarily well planned. You know, things are not repeatable, not documented really well, versus, and so when that happens, you know, what we see is generally we have an idea for a product, we implement the system, we don't do a lot of testing of that implementation, we try to get it into the lab as quick as possible, and then you get into this thing we call the lab trap, where it's hard to debug in the lab. It's hard to know when you've tested everything in the lab. And so it's hard to know when you can get it out of the lab and get it into a customer's hands. Whereas a structured process is where you spend some time after the initial idea in a planning phase. You know, you really focus on requirements and requirements tracing. You really focus on you know, how you're going to verify as well as how you're going to implement the design. It's usually a very well documented and well reviewed. There's traceability of the requirements. And the idea is that the verification stage is happening at the same time with the coding and development. And the idea is to spend to not need to spend a bunch of time in the lab and to deliver a more structured product. Just as an example, we worked with a leading aircraft integrator who was having really long schedules in the lab. They were saying that it would take forever. They began to apply a much more structured approach, and the result over the last couple of years is that 23 of 25 of their FPGA products they brought up in the lab, got them working and out of the lab in a day. So what we're going to do in this webinar is introduce some of those structured design flows. And so the main thing is here to do this pre-design phase, where we do a bunch of planning. We really focus on creating good requirements, tracing requirements from one level of, maybe from like the system level to subsystem level to board to chip to, having a layered set of requirements and then tracing all the requirements within there. Conceptual design is doing a little bit higher level modeling of the design that may or may not be done. The requirements management and tracing we'll talk about tracing those requirements all the way down to the results of your simulations, to code coverage. We'll touch a little bit on CDC analysis and those pieces of the design. So, as I said, the first thing that we really need to do is focus on requirements and requirement tracing. And this is really that planning phase. If you're going to build a house, you don't just start, laying a foundation without a solid set of blueprints. And that's really what we're saying, that you need to do the same thing on your FPGA design. So what goes into a good FPGA plan is, you normally start at the top level, at the system level, define what your system needs to do, then break that down into the hardware requirements, the software requirements. The hardware requirements might break down to a board spec and an FPGA spec. So you really need to focus on those. You need to declare what the team is, what all their responsibilities are. Have reviews throughout the cycle to make sure that we are meeting the requirements, that all the requirements are covered from each level to the next. You really map out the processes, the procedures, the tools that you're going to use. You map out the how are we going to develop this, and then you set a schedule and, make sure that if you do have something like a DO-254 or an ISO 262, in that case, you're going to have auditors who are coming in to audit the state of your project at various points within there. So you really need to address how you are going to get through those audits and pass those audits and reviews, both internal and these external audits. So it starts out with that planning document. I'm going to go through some of these slides. I've got a whole bunch of slides on the planning documents. I'm probably going to go through these fairly quickly because you will get a PDF version of this document and you'll get a link to it. So I'm not going to, spend all the time, but that planning document is going to be, you are going to have a unique part number for that FPGA that's being developed. You're going to have revision control on this document. You need to identify all the participants in the team and, make sure that they're doing approvals at each stage. As I said, you're going to have a revision history that's part of this document. If you look at, for instance, the DO254, but also the ISO 262, they, say that you need to have a table of contents within that document. You're going to clearly state the purpose of the document, describe each of the team members, what their role is, functional description of the FPGA, and then at some point, let's see, so you're going to detail the hardware design process, how the verification is going to happen. If you have a certification or an audit, you're going to identify the auditor, what audits are going to happen, at what point in the project those are going to happen. And so that's all kind of the introductory stuff. And then you get to the point of requirements. So that first document was just laying out the process for your design. And then at that point, you're going to start to have, say, like a customer level requirements document. This is what the customer is expecting from us. You're going to have a hardware level, maybe. You're going to have a subsystem level, a module level, an FPGA level. And what you need to do is be showing that here are all the requirements in this document, and how do they map to the requirements here? And then how do those map down to the subsystem level document? How do those map to the next and down to the FPGA, et cetera? And then also, what is the validation that is done at each level? So this is kind of an example of what's called the V process. So design assurance is really about making sure you're delivering a design that performs the requirements as they were laid out. And that intended function is laid out in the requirements. And so for each requirement, you need to capture it, you need to review it, it needs to be managed, and it needs to be traced through the different levels of requirements. So what is a requirement? It's a condition or capability that the use of, an objective of a problem that needs to be solved. That's kind of, it's a specification of what should be implemented, maybe is a better, a description of desired behavior of a property or an attribute. So in a lot of ways, the requirements, what they are is what's in the head of the designer or the project manager or whatever. And what this talks about is how to turn that knowledge that that person has into effective requirements. And what is an effective requirement? It has certain characteristics. It needs to be complete, correct, feasible, meaning it's implementable. It needs to be necessary. So you need to really, it shouldn't be something that's not really necessary. It needs to be unique, prioritized, so that you can, figure out what's important to make sure is implemented versus what's nice to have. Clear, verifiable, meaning it's testable, and traceable. So that's kind of, a consideration of a bunch of things. So if you look at a requirement, it's going to have certain attributes. So every requirement has a unique requirement ID. And in this case, what we've done is we have this string right here, which is unique to the document that this requirement is living in. And then we have a number that is unique for every requirement within this document. So within a project, no other requirement will have this requirement ID. The requirement text spells out, what the requirement is doing And using the word shall is usually a good way to construct the requirement so that it meets those implementable, feasible, etc. Just by using that word in the requirement text, it helps to set it up in that way. Optional things that can be part of a requirement are things like, and my arrows are a little off here, looks like, attributes. So you can have things like priority, safety critical, other things can be an attribute of a requirement. So those are optional. And then the coverage tag is, we will always have a coverage tag except in the very top level requirement document. So every requirement is covering something from a higher requirement document unless it is the root system spec requirement. So first thing I'm going to do is show you an example of a really bad requirement. So this is requirement number 1. The DDC shall be configured to any depth or width, but will be 256 deep and support a 64K with memory with sufficient address and data bits. It will need some kind of reset function. It also, you should be sure to avoid collecting crossing issues between the CPU and the memory interface. So there's a bunch of problems with this. First of all, that requirement is about 5 requirements all buried together in one. So that really should have been 5 different requirements. Other things that were wrong with that is that, we did not use the word shall, so we didn't really set up those requirements to be implementable. We lumped a bunch together. There was stuff in there that wasn't really a requirement. It was more theory of operation, which, should be in the document, but it shouldn't be part of a requirement. You shouldn't use things like sufficient, enough, very fast. Those are unverifiable things. That's unclear what that means. You shouldn't cast things as negative requirements where it said avoid CDC issues. Right here is it shall support 2 independent clock domains. So anyway, that's kind of, first off, something that's sort of a bad requirement. So where do we store these requirements? And you can store them, in various places, Office documents, MS Word, Excel. That's, oftentimes you're writing a requirement document and, it is natural to put your requirements in there. But without something that hooks those together, you're manually generating those requirement IDs. So there is the possibility of creating redundant things. You need to do the tracing manually, and that becomes, a fairly complex system of creating and tracing those requirements. Another place, especially in the Mildera world, is you'll see requirement capture tools like doors. And those are really good at capturing requirements. What they're not good at is breaking out of this requirement. The problem with doors is everything that lives indoors has to be a requirement. So you can't really have a document with some theory of operation, but then you have requirements that are embedded in there. So it is a really good system for capturing the high-level customer requirements, but at some point you do want to break down documents. You want to start tracing to your RTL code and to your test bench code and to your test bench results, etc. And that is not easily done with doors. The other thing about doors is it is an enterprise level system. It takes an expert to run it. There's a lot of overhead. and it's really expensive. So what we'd like is some way to have both a high-level requirements capture system like doors. EDA Direct also sells a tool called Polarian, which is got some of the doors functionality in it. Currently, it still does not do well at tracing into Word documents and into code and into simulation results. Mentor is now owned by Siemens, and Polarian is a Siemens tool, so we are working toward getting some of that traceability, some of the rec tracer functionality in stores, but I'd say that's still about a year off. So it makes sense to use both rec tracer and doors still at this time. So really what requirements tracing is about is verifying that your implementation of the design performs the desired function. And it's about tracking that requirements traceability, controlling as things change, as edits happen, that we make sure that we update things, so tracking changes, communicating when a change happens to the people who need to implement those changes, impact analyses of saying, if I change this high-level requirement, what is the impact downstream of doing that, and communicating it to everyone. So how do we trace the requirements? And that is done right now. Mentor does that through a tool called Rec Tracer. And so what's shown here is a kind of a hierarchy of a fairly simple FPGA product. And what we see here is we have a doors database. So someone, this is probably a middle project. The customers, they captured the high-level system requirements in doors, but then they subcontract it with another company who was going to design this FPGA. And so that company created a design spec for that FPGA, and then a test plan of how to test that FPGA. And then here's the RTL code that implements this design spec. And so for every requirement in this high level that flows down to an FPGA, I have to show that I've covered that requirement in my design spec. And then I have to say how I've implemented each one of these requirements. And I also, in my test plan, have to say how I'm going to test each one of these requirements. And then I have to trace down to my test bench code that says, okay, here are the tests that I run, and when this test is passed, that requirement is covered. Right here is the text logs that come out. So I set up my test bench to not only say this is the test I run to test that, but it also writes out results so that I can verify that that test passed. And then I might also bring in things like my code coverage results. I might bring in, if I have assertions and cover point and cover groups, so system verilog functional coverage objects, I might bring those back as well. And so this is kind of what we do to make sure that this all happens correctly. So let's look at this requirement, and I'm saying this is a requirement that right now is in my design spec. So in my design spec, I've got a requirement that says the DVC shall provide 256 words of cache memory. In my RTL code, I actually put in implementation strings. So I'm put in -- implements, and this is in my VHDL code, and it's just basically saying that somewhere in this entity architecture that this requirement is met. And that's kind of the level that I suggest most people would go to. So that's that implementation tag. That requirement also probably has a coverage tag that's saying this requirement right here is covering this requirement that comes from this higher level. So that's showing that traceability. And so you put in these things, and then RecTracer becomes the hub that connects all of these documents together, connects all of these results together, and produces some report. So if indeed you have an enterprise level requirements capture tool like doors, that can feed into RecTracer. So RecTracer basically is peering up into that doors database and saying, what are the requirements that I need to cover? And then you have your Word documents, your Excel spreadsheets, whatever, that are then connected up into that doors. You get your RTL code, your test bench code. Maybe you have some C++ models, other things like that. RecTracer can actually connect to our DX Designer board design tool and the constraint editor system within our layout tools. It can connect into the synthesis tools. It can connect into MATLAB, to other modeling tools. Any text logs that these tools produce, you can bring those back in and have RecTracer process those text logs. Again, any coverage objects like code coverage or functional coverage, cover points, cover groups, that coverage can be brought back into RecTracer, and then RecTracer becomes the hub that tests all that connectivity and puts out different reports. So it can put out, coverage reports that are generated by Questa. It can, show you the traceability. It can create what's called traceability matrices, which is a big thing that these auditors are looking for. And so really it is a tool to facilitate capturing requirements, creating the requirement ID. If you need to put in certain attributes, it can do that. There is a coverage generator that allows you to connect back up to the higher level requirement document. And basically, it facilitates that capture and that traceability. So a real simple example is, let's say in doors I had these 5 requirements. And then I've got this design spec that I wrote in Word, and I've tagged some requirements within that design spec, and then I've gone through and I've put in these coverage things on each of these requirements. And you can see, like, this requirement says, if this is done, this requirement is met. Here, I've said this particular requirement takes these 2 design specification level requirements. So you can have a many-to-one match there. You can also have a one-to-many. So one requirement might come back up here and cover multiple things up here. So it's not necessarily a one-to-one. And then here I've got my RTL code. And again, I'm putting in those implementation tags. And so I'm saying, which entity architecture, which module is implementing each of these requirements in my RTL code. And once you have now this traceability, you can look at it and you can say, okay, you know what? Where are these 3 requirements implemented? Are these hardware things? Are these FPGA things? Or maybe these are software requirements and I have to have some other document down here that's covering these 3. On my implementation side, I can see I've only implemented, or at least I've only said where I implement 60% of my requirement. And so I've got to either write some more code or go down and put the implementation tags in existing code to say where these other two things are implemented. And then you can look at this and you can actually like say, okay, wait a minute. What is this module doing? It doesn't seem to implement any requirement. Why is it here? Is this redundant? Is this code that should be in the design? So that's, you know, one thing that RecTracer starts to give you is that ability to manage. There is a concept within RecTracer of taking snapshots of your design. So you can kind of say, like, maybe, you know, I take a snapshot and I say, you know, on January 22nd, I took an alpha snapshot and this was the state of the requirements. And then things have been progressing along and I've made some changes. And so today, February 28th, I kind of take a look at my design and I'm going to say, you know, what's the difference between the current state of my design and that alpha state that I captured? And it will flag anything that is different between those snapshots. So I can immediately see that, oh, you know what, this requirement went from being a high priority to a critical priority thing, and I've added that it also covers some other high level specification here. So you can take these snapshots, and then at any time you can do these comparisons. Again, this can be useful in those audits that you have with the auditors. So another thing that you can get once you start to have this type of information is what's called impact analysis statements. So we already kind of talked about keeping track of where we are, what we got to do in the project. But now let's say the customer comes to us and he says, you know, I want to change these two requirements. And by having this full impact or full requirements traceability, and, you know, if I showed this where it flows down even further to other documents, I can tell them, well, yeah, you want to make some small changes to these two requirements, but I'm looking at, you know, the impact, and just to flow down to the design specification, you changing these two things here actually means I've got to change 3 down at this level. And then in my implementation, that's going to affect a whole lot more code. So it can help you to come up with the cost of implementing requirements changes and feed that back to your customer and say, look, if we make these changes, that's going to cause a 3-week slip in my schedule. Is that, you know, are these critical enough changes that we need to do that? And then finally, you can generate all these different types of reports that are used either in your internal reviews or in your auditing sessions with your, in DO-254 terms, your designated design representative. So the traceability matrices is one of the main reports that it can generate. So currently this is showing between this product level requirement and the design specification. And it's just showing the traceability of those. And so it's basically, you know, giving a matrix that shows this representation of the coverage. Now this is just between 2 levels, but I can actually, if I have multiple levels, so if I have, you know, a system level requirement down to the product requirement, down to the design spec, down to the test plan, etc., I can do a traceability all the way from this level down to some sub level, and I can still show that traceability, and it will show me all the traceability to get there between those. So these reports are very customizable, different kinds of output format, and we've really worked with DO-254 representatives and ISO 262 representatives to make sure that we are creating the reports that they require in order to give a sample approval on their audits. This all represents the live current state of the project, and it generates all the artifacts that are going to need for these safety compliance audits. So the summary here is that RecTracer is providing that last bit of connection between your requirements, your requirement documents, and then your FPGA implementation code, your test bench code, your test bench simulation logs, and the UCDB database. It can also be used on the PCB side of things. So there's a whole bunch of other connections there. So we really have found that customers who are facing these compliance safety standards for different industries, so civil aviation, automotive, I forget exactly what the medical FDA standard is, or the transportation standard, the banking standard. There are all these different standards, but they're all fairly similar, and we've worked with representatives to make sure that we are creating the artifacts that are required to meet that. So the next thing we'll talk a little bit about is the idea of code coverage. So one of the things that is required in most safety critical standards is that once you've implemented your design and you run some tests on it, that you have to show 100% code coverage on your design. And so code coverage is just really a metric of how well does your test bench implement your code, or excuse me, how well does your test bench exercise your implementation of the design. So it's really, you know, it's line coverage, statement coverage, branch coverage, all these different things. And, you know, most safety critical standards say you have to have 100% code coverage, or you have to have a exclusion for every non-covered object. And that exclusion has to explain why that code is not or cannot be covered. So code coverage is built into most, you know, simulators, Model Sim, Questa, VCS, whatever Incisive is called these days. And it's really just a measure of a lot of different things. Statement coverage. Have I executed every executable line of code? Branch coverage is, have I branched true or false in every if statement? Have I taken every possible branch in my case statements? So those are kind of the easy ones. Conditional coverage is a little more complex in the sense that, let's say I have an if statement and I have if A or B, then branch true, else branch false. So I could have 100% branch coverage. I have branched both true and false. But if A or B, the conditions are, I should branch true when A is true and B is false. I should branch true when A is false and B is true. And I should branch true when both A and B are true. So there's 3 different ways to branch true, and there's only one way to branch false. Conditional coverage does that additional layer of peering down to make sure all the possible conditions in all of my branches. Case statements, if you have multiple cases that branch here, it's going to make sure that you branch for every one of those cases. Finite state machine coverage is, you know, honestly, you can probably infer finite state machine coverage from most of the, like the conditional coverage, etc. It's just, if you have a finite state machine, it will give you a visual representation of that finite state machine and show you both the state coverage. Hopefully you can see that we've never hit this control. It's circled in red, and you can see that there are different branches here that I've never taken this branch. I've never taken this branch or this one or either of these. So that's finite state machine coverage. Focus expression coverage is really a type of conditional coverage. And then toggle coverage is, have you toggled all of the bits in your design, all of the registers, have they both been a 0 and a 1?
I'm in the middle of something.
So, this is kind of the joke of, why do you need 100% statement coverage? Well, you've got a roof and you got 98% coverage and it rains, you're going to have water in your house. That's kind of the idea of code coverage. You have written all of these different branches, all of these different conditions, and in theory, you have all these different conditions to branch true for a reason, and if you haven't tested one of them and it's incorrect, that's probably going to be the critical bug that, causes your mission to fail. So verification management is kind of about getting that idea of what's been covered, what still needs to be covered, how long is it going to take, how can I improve my process. It's really that last mile problem is the biggest thing. It's easy to get 90% code coverage. It's really hard to get 95% coverage, and it can be really impossible to get that last 5% of coverage. And so, is there something we can do to help with that coverage challenge? And, it could be that you're using IP in your design, and that's configurable IP. And because of the way you've configured the parameters on this reusable module, you will never hit certain branches of code. And the question is, do you fully understand that? And will you spend a lot of time trying to get coverage on things that are uncoverable? And it can lead to a lot of wasted effort. And so, the normal way to try to do this is you would run your test bench. And, I'm saying it's a UVM test bench. It could be a set of directed tests. It's whatever. But you run that, you end up with these coverage holes, and then you look at each of those uncovered objects, and you either try to come up with a reason why those are uncoverable, or if you can't come up with a reason they're uncoverable, you go back and write some more tests and run your test bench again and see what's been covered and what hasn't been covered. So Mentor has a tool called Cover Check. And what Cover Check's whole purpose is that you run your simulation that first time. You come up with those things that are not covered. And then Cover Check is based on our formal verification engine. And it will look at all of those uncovered objects, and it will try to do a state space analysis where it is saying, I'm not going to run a simulation. I am going to calculate every possible state that this design could go into, and I'm going to try to either find that these things are uncoverable and then give you the reason why so that you can generate these waivers, or it will, whoops, I went the wrong way, sorry. Or it will say these are coverable, and let me give you an example of how. So the way it really works is, like I say, you run your test bench, you get the coverage results, and then Cover Check will either find that those are uncoverable objects and generate some exclusions, or it will produce what's called a witness waveform. So it will say, if you apply this stimulus to your design, this is how you get that line of code covered. And so it is basically generating an example of the stimulus for you to help you to go back and guide you to create the stimulus you need to cover those objects. And that's really kind of showing the same thing. And then as far as, you know, it's going to go through each of these different types of coverage and figure out, you know, what is coverable, what isn't, and help you to generate those exclusions. So, you know, this was kind of the ROI on that. We had a customer and they said, you know, they had a certain design. There was 3,000 uncovered objects. And those objects were, you know, either lines of code or branches or conditions or whatever. And they just did a rough estimation that it would take about 15 minutes to analyze each of those 3,000 uncovered objects, which was about 4.5 man-months of effort. And then with cover check, they either got the exclusions almost, you know, cover check is a tool that you run, and they either got the exclusions or they got the witness waveforms, and, you know, it took them a week or two to get that coverage closure versus the 4.5 man-months. So another thing that we kind of are starting to see in the safety critical world is this idea of hackability of your hardware. There was, you know, I don't know if you saw this. There was a study done where these hackers, they actually were able to produce a CD that somebody slid into the CD player of a Jeep Cherokee, and there was some malicious code on there that allowed them to basically get in and get control over the CAN bus, and they were able to actually get control of steering and braking remotely on this vehicle and cause it to steer off the road, and, you know, trace that back, and it turns out the root cause of it was an actual hackable spot in the hardware code. In the banking world, you know, you want to make sure that your electronic wallet is not vulnerable to attack so that somebody can get a hold of your money. And then the ultimate extreme is kind of this, where your smart, you know, vacuum is threatening to, you know, blow dirt all around your house if you don't pay them off. Your smart trash can won't let you throw away the trash. Your smart dishwasher is, you know, bribing you. Your heater won't heat up unless you know, pay it off. So that's kind of the joke there, the Internet of Things. The other place is in the safety critical world is not necessarily for malicious hacking, but two systems that should never happen at the same time. You should never be running down the runway with the flaps up ready to take off and then have the air brakes come on at the same time. So things like that, and it's really, you know, there's a lot of concern and a lot of ways of trying to deal like with light hacking. And, you know, a lot of that is at the software level, but, you know, the real root of your trust begins down here at the hardware level. And so what Secure Check is about is creating that root trust at that hardware level, making sure that there is no way to access certain areas of your design except through the specified ways that you said. So for instance, you know, let's say you have some kind of an encryption engine in some kind of system, and I've declared, actually, you know, let's say I've declared that the encryption engine uses those encryption keys that are stored right here. And right now, I believe the only path that I should be able to write to these encryption keys is if I'm doing it through this microprocessor interface. And what secure check does is you'll declare that I think the encryption engine should be able to access those keys. I think I should be able to access them through this path, and then it will go through and use that formal engine of state space analysis, and it will, in this case, it found there's actually a backdoor path that I can come through this Ethernet controller or through this AXI controller, and I can go through my DMA system, and I can actually get in there and get access to those. So Secure Check is a tool about making sure that you don't have access to those. And kind of the traditional methods are through, I'm not too worried about it because, this is not worth somebody's trouble. So that's the security by obscurity. White hat hacking is, okay, let's have a hacking expert make sure that they can't get in, or expert in detection. You can try to do, testing with directed testing or constrained random, but none of those things are exhaustive, and they can take an awful lot of time. And so, like I said, with Secure Check, what you do is you go through and you program the paths that you believe should exist to certain areas, and then it will use its formal state space analysis, and it will try to find backdoor paths, and it will either show you that there are insecure paths, or it will say that these paths are secure. Not going to spend a lot more time on Secure Check. So the summary there is that it's all about finding either sneak paths for someone hacking to try to get to things, or making sure that two events can never happen at the same time. So where are we on time? We do have a few more minutes, so I'm going to talk really quick about clock domain crossing. If you look at this study, these are some studies that we do with Wilson Group every couple of years, and I should have the 2018 data any day now, but it basically shows that so this is in the ASIC world, that, misdesigned functional bugs are the biggest cause of an ASIC respin. But, the second, or at least in the 2016 study, the third biggest reason was clocking issues. And oftentimes that is clock domain crossing type issues that have caused ASICs to be respun. And then if we look at the FPGA data, it is clearly the second most, common problem is clocking issues and clock domain crossing issues. And when you look at modern systems, you'll have 1, 2, 3, 4, 5, 6, 7, 8. This is a fairly, not super complex system, and there's 8 different clocking domains, and so 8 different places that data is crossing from one domain to another, and probably thousands of signals are crossing from one clock domain to another. So doing that clock domain analysis manually is very difficult. And, anytime a signal crosses from one domain to another, there is the possibility of metastability. And metastability is that this signal will hit the setup and hold violation, because these clocks, even if they're nominally the same frequency, they're going to have some slight difference, which means at some point this signal will be changing within the setup and hold window of this clock. If you think about metastability, the best analogy I can come up with is you are driving down the street and you are about 50 feet from the intersection and the light turns from green to yellow. And you're right in that range where you're like, can I get through? You know, what are the conditions? Is it a little snowy out? Should I hit the brake? Should I hit the gas? And I had a lot of people say, I always hit the gas. And to them, I always say, okay, move another 25 feet down the road. At some point, you are going to hit that metastability moment where your foot is wavering and you can't decide what to do. So what our CDC tool does is it does a complete analysis of every signal that crosses from one domain to another. It makes sure that there are synchronizers in place for every one of those signals. If there is a structural issue, so in this case, there's a missing synchronizer, or actually here is a synchronizer. In this case, it's not a missing synchronizer, but there is logic between the last flip-flop and the synchronizer, which is a no-no. That's a structural issue. So first it does that structural analysis. And there's a fair number of tools that do that structural analysis, but I think we have a really nice debug facility for the structural analysis part of it. The next thing is, even if you do have the proper logic in place, so I'm passing this data signal from clock domain A over to clock domain B. It's a 16-bit wide signal, and so the way I pass it is I pass a sample, a control signal that says it's safe to go ahead and grab that signal. And so I set this mux, the data flows through, I capture it on this clock, and then the control signal goes away and it's locked into that flip-flop. So now there's a protocol that has to be met. And that protocol is this signal right here better not change, better be stable for the entire time it takes to send the control over and then to have it go away. And so now I have a timing protocol I need to meet. And does the circuitry that I have, is it possible for that to violate that timing protocol? And so there is where just a simple structural analysis no longer works. We need to do a deeper analysis. And that can be with that formal state space engine, or that can be with some simulation. And so what our CDC tool does is it first does the structural analysis, shows you where the problems with structural analysis is. Then it has the things that it's like, okay, this looks good, but I can't prove the timing protocol. So let me run the formal engine and see if the formal engine can turn that into proofs. And so it'll take some of the things that are still question marks, and it'll say, okay, those are proven, or, oh my God, here's a problem, you need to fix this. But then you might still have some things left over that it wasn't able to either prove or disprove. So then those, what it does is it creates a protocol assertion that's going to analyze the timing, and you use your test bench and run simulations, and then those simulations, you'll collect enough information to either find violations or promote those to passes. And so that's the second step. So the first step is the structural analysis. The second step is the protocol analysis. And the third step, and this is one that I don't think any other tool on the market does, and this ISO 262 is, we're the only tool that ISO currently certifies to do reconvergence, although I don't know why that's right there. And reconvergence analysis is that I'm going to examine this signal path. So I'm going from the purple domain to the green domain. And I've actually done the analysis on this path. I've proven that that's a proper synchronizer. I've proven that I can't violate the timing protocol. And then I've done the same thing right here. So this signal right here is okay. But if you look at that, that signal goes through some other combinational logic, goes through some sequential logic, and eventually these two signals come back together through some logic cone. Now, they had some timing relationship with each other back here in the purple domain. And the problem with a synchronizer is that there is unclear timing. It could have plus or minus 1 clock cycle timing difference after it gets through this synchronizer structure. So by the time these two signals come back together into this logic cone, whereas they might have been on the same, generated on the same clock cycle back in the purple domain, they could be plus or minus 1 cycle out of phase right here. And does that matter to this logic cone? So what our tool does is you set the reconvergence depth you want to test for, and then it will do an analysis of all the potential reconvergence paths, and then it will do some analysis to make sure that you don't have problems when those signals reconverge. And as I said, all of our simulation tools are certified or qualified, excuse me, by the ISO 26262 standard. So the automotive standard, they actually do tool qualification. So our simulator has done that, but so has Cadence, and so has Synopsys' simulators. On the formal side, these state space analysis tools, no other formal tool has gotten ISO 262 qualification. And we've had this for about 2 years now, and there's still not another tool on the market that has gotten the qualification from the ISO 262 board. And so, that's kind of our proof in the pudding that our formal tools are a step above some of the other ones that are on the market. So anyway, the summary on CDC is that it will help you find your clock domain crossing issues. Clock domain crossing issues are notoriously hard to find in the lab because they only occur once in a while. So, if you have or suspect that you could have CDC issues, Questa CDC is probably I used to say Cadillac, but probably now the BMW of clock domain crossing analysis tools. So that's all I was going to present today. I can drop back and see if there's been any questions that have come up in the chat window.
Doesn't look like there's any question, Walter. So
okay.
Great. Yeah, some of these reconvergence is very useful. I just want to add to what Walter said is that if you have FPGAs and you have routing differences and speed differences in devices, one time you may see, one time you may not see without the conversion. With conversion, we actually can help you, with those ranges. So, and this is unique. No one else has this solution right now. All right. With that in mind, any last question from the audience? If not, we will close the webinar. And thank you for attending. As I mentioned before, this is recorded. And contact my email in here, Kung, C-U-O-N-G, @eDayDirect, if you'd like to have a copy of the presentation. Okay? And
yeah, I will have a PDF version of this available for anybody who would like it.
Yeah, actually, Walter, yeah, you can send both, and I'll send the PDF to a customer.
No problem.
All right. All right. Thanks, everyone.
Right.
Thanks, Walter, and have a great day.
Okay. Thank you.